Okay, we're in multivariable calculus. We're looking at double integrals, but not over rectangular regions. Double integrals over just general regions. These regions will have some kind of function who is the upper part of the region and some kind of function who is the lower part of the region. That's one option. So the upper function is called g2 of x here, and the lower function is called g1 of x. There'll be two different ways we can integrate. We can either do y first or x first. This here is y first. It's dy dx. It's a vertical slice who then gets moved horizontally to sweep out your volume. What I like to do with my vertical slice, or any slice that I make, is put two circles at the ends. Those circles are very important. Those circles end up as your inside integration bounds. When we have a general region like this, no longer will we have bounds that are numerical. Now we're actually going to have a bound that is a function. And so there'll be some multivariable function. This is on the floor. This is on the xy plane. And we're integrating some multivariable function above this region. We'll move this from left to right. So x equals a and x equals b end up as the lower limit and the upper limit on the outside integral. The outside integral always has numerical bounds, but the inside integral can have bounds that are generally functions. Functions could be constant, the functions could be just general functions here. So I have g2 of x as my upper function throughout the region. I have g1 of x as my lower function throughout the region. They then correspond to my upper and lower limits of integration on the inside integral. dy dx is the vertical slice moved horizontally. Generically, the symbol is f of xy dA. And dA stands for, well, you have a choice. You can either do it dx dy or dy dx. We'll learn later that you'll have a third option as well. Okay, generically, we'll put a little r down to represent the region. So the purple region is the region R. And now we can get more specific and say that we're going to do it as dy dx. We're going to have the inside bounds be the g1 is the lower, the g2 is the upper, and then the outside bounds be the a and the b. It's what you move from left to right. Okay, so this is a dy dx setup for a double integral over a general region. Let's see an example of this used. We have 4xy minus y cubed is our multivariable function, and the region R is the region between the curve y equals root x and y equals x cubed. Got to be able to graph these. So first up, y equals root x is standard kind of a parabola on its side, only the upper half. And then y equals x cubed is a standard kind of a shape here. We're only drawing the one part where we have in the first quadrant. Somehow this should say perhaps in the first quadrant to be precise. But the root function only lives in the first quadrant. And so we're only talking about this region here. This will continue on. Both these graphs will continue on. But that'll be unbounded there. We're talking about this bounded part here. And that's our region R. And it fits what we just said. There's a defined upper function, a defined lower function. We should do this as dy dx. Let me even go further and put the little circles at the ends. Okay, it turns out that the square root function is the higher function and the x cubed function is the lower function. If you put a number like 1/4 in, the square root of a fourth is a half, but the cube of a fourth is 1/64. It's smaller. So we're going to do this dy dx. The blue is basically going to represent like what we've already swept out, and now we're going to continue to sweep from left to right. So this is dy dx. Okay. So then the bounds on the inside are actual functions. Root x is the upper bound on the inside, and x cubed is the lower bound on the x side. We have the upper limit and the lower limit. And then this moves from left to right. We start at 0 and we're done at 1. X cubed on the lower limit inside, root x on the upper limit inside. We're going to move from 0 to 1. So 0 and 1 are the lower and upper limits on the outside. The function goes on the inside. Technically, I feel like I should put some parentheses here. Our first integral is y. How do you do an antiderivative? Well, how do you do a derivative? You hold the other variable constant. Same thing for antiderivative. Hold the other variable constant. So I want to integrate with respect to y. I have 4xy. I treat that x like I treat that 4. Leave it. Focus on the y. Y squared over 2 is the antiderivative of y, and then you just put the 4x on there. 4x times y squared over 2. And then the other term, that's just a y only term, that's y fourth over 4. So technically what's missing there is we had a 4x times y squared over 2, and that 2 turned the 4 into a 2 for us to arrive at the term 2xy squared. Okay, you do that integration, and now you have bounds that are functions. If it helps you, you can put in what the function, like y equals root x and y equals x cubed, just to remind yourself that you are replacing y. Your y will be replaced by root x for the upper limit. Your y will be replaced by x cubed for the lower limit. And so the root x gets squared. That's how we got that x. The root x goes to the fourth. That's how we got that x squared. Then we have to put x cubed in, and that's the lower limit. So x cubed gets squared. That's x to the sixth. And it's already times a 2x. That's how we arrive at this 2x to the seventh. And then x to the 3 goes to the fourth power, and that's how we arrive at that x to the 12th. Well, something nice happens here. The 2x squares can be put together. 2 of them minus 1/4 of them is 7/4 of them. And now you're in a Calc 1 integral. Polynomial in nature, so just antiderivative. And the bounds are nice, 0 and 1. And so we get x cubed over 3, so that's going to give us 7x cubed over 12, x eighth over 8, so minus, instead of saying minus 2x eighth over 8, we say that the 8 can cancel the 2 and give us x eighth over 4. And then finally, x to the 13th. 13 times 4 is 52. Let's put a 1 in. 1/12 minus 1/4 plus 1 over 52. Officially, what's going on here is that there is a lower limit of 0. I feel like we should put these two together. They work out nice. 12 is the common denominator, so we can put these two together by timesing by 3. 7 minus 3 is a 4, and that's over 12. That 4 over 12 can be reduced to end up as 1 over 3. So now 3 and 52 is going to have to be 156. So we're going to times by 52, times by 52, times by 3, times by 3. Final answer, 55 over 156 represents the volume under our surface and above our region R. Let's cut this video short. In the next video, we'll look at dx dy.